Okay, so in the previous section you looked at two types of line integrals, and now we're going to think about a new type of integral called a double integral. Okay, and this is a step towards being able to calculate volumes and surfaces of three-dimensional objects. Okay, so how do you calculate the volume of a sphere? All right, we'll get to that in section 6. For now, we're going to think about functions of two variables only. Okay, and we're going to generalize first by thinking about a function of a single variable, f of x. Okay, and you know that the integral of f of x dx between 2 points a and b, okay, represents the area under this curve. And the f of x dx on its own represents the area of some strip of width dx and height f of x. Okay, so this is the sum of all strips. Strip of area f of x dx. Okay. All right, so we're going to now extend into 2 dimensions, so not just x, but let's draw an x and a y-axis. Okay, and you know that if you've got a function of x and y, this is a surface. Okay, so z equals a function of x and y. Maybe it's some surface. Okay, so remember, this is the height above the xy plane. Okay, so you choose an xy coordinate, you plug it into this function and it gives you a value. That's the height. Okay, so this point is a point on the surface which is a height z above the x and y value you've chosen. Right, let us think about a little dx and dy. So we're thinking about a little rectangle in the xy plane. Okay, and this, we're going to think about some region S. Okay, some region S that contains this rectangle. Okay, so looking down from above, this is the xy plane. This is some region S. And we've got a rectangle of width dx and a dy. Okay. Dx, dy, we call the element of area. Okay. The area of this rectangle is its width times its height. Okay. Dx times dy. Right. If we think about the height of the function, okay, then we've got a rectangle on the xy plane that's dx wide in x and dy wide in y, and the height is z. So what's an area times another length? It's a volume. Okay. So we're going to think about f of x, y, that's the height, times this area element. Okay, so this is height times area. Okay, and this height times an area is a volume. Okay, so this thing is the volume of this column. And if we sum over all the columns in this region S, then we get a double integral. Okay, we get 2 integral signs. It's over the region S. We've got our height of our function and the dx dy. Okay, and this thing is the total volume under the surface. in the region defined, okay, this is some closed region in the xy plane. Okay, so this is our double integral. And we'll see how we can calculate these double integrals in a second. Okay, but keep in mind that this is just the volume of the column, and then the integral, we're summing over all the columns, okay? So there's columns along x, and there's columns along y, okay? And we're going to add them all up. So we're repeating this little dx dy column along x and along y. Okay, and we're adding them to get the total volume. Okay, so what is this region S? Well, it's easiest to choose S to be a rectangle in the xy plane. Okay, maybe from A to B, C to D. Okay, and in this case, we can write I as the repeated integral, where we do the integral over x first. So we do the integral over x from A to B, and then we do the integral of y to C to D. Okay, and what this means is this integral is done with respect to x, holding y constant. Okay, so this is thinking about little strips at constant y, and we add these all up, and then we add all these horizontal strips when we do the integral dy. Okay, and you can, it doesn't matter which order you choose. This is equal to the integral dx from A to B, dy from C to D. Okay, so this integral is done first, and then this one. Okay, so that's how you read this. Oh, and it doesn't matter if you've got the dx in front or after. Okay, but it's the inner integral that's done first, and then it's the outer one. Okay, so if we integrate f of xy over dx, we're integrating out the x. So this will give us a function that just depends on y, and then we integrate that function that depends on y dy. All right. In this case, we integrate with respect to y first. This gives us a function that only depends on x, and then we integrate that function that depends on x with respect to x. Okay, so we'll look at an example. So let me just clean the board, but this is our double integral. Okay, so say hello. All right, let's think about an example. So let's think about the function of two variables that is equal to x plus 2y. All right, and let's think about the double integral of this function. So we've got the height of the function and this area element, dx dy, around the region S, and the region S is going to be defined as the region between x is 0 to 2 and y goes from 1 to 3. Okay, so in the xy plane, our region S is a rectangle. Oh, and it's going from x equals 0 to x equals 2. and it's going from y equals 1 to y equals 3. Okay, so this is our region S. Okay, and if we make a 3D plot of this function, x plus 2y, in this xy region, then it looks like this. It's a house with a monopitched roof. Okay, so we've got on the top here the function showing the x, y, and z axis, and then at the bottom we've gone around the back and we're inside the house looking at the roof. Okay. Right, so the integral, the double integral on this region, it's the volume of that house. Okay, it's the volume underneath the roof. So how do we do that? Okay, so our integral is the double integral of x plus 2y dx dy. Okay, and x is going from 0 to 2. And so the integral of x is inside, so the limits, so this first integral, the limits go with x, and then the outer ones go together. Okay, the limits of y are 1 and 3. Okay, and we just do this integral by first doing the integral with respect to x, holding y constant. Okay, and we're going to do that first. So this, we leave the integral with respect to y untouched. Okay, and we do the integral with respect to x, holding y constant. Okay, between 0 and 2. Okay, so this is the integral of x plus 2y dx. Okay, between 2 and 0, so we get x squared over 2 plus 2xy. And we need to evaluate that between the limits of 0 and 2. This is x equals 0 and x equals 2. Okay, so this equals the integral of dy between 1 and 3, and then this function is going to be a function of y after we put in the x limits. So it's x squared when x equals 2, so this is 2 squared, which is 4 divided by 2, so that's 2, plus 2 times y, 4y. Okay, and then when we put x equals 0, both terms go to 0. So this is our function, and you see it's a function of y. Okay, we've integrated out the x. So now we just need to do this integral. Okay, it's equal to 2y plus 4y squared over 2, 2y squared. Okay, between y equals 3 and y equals 1. Okay, so this equals 2 times 3, which is 6, plus 2 times 3 squared, which is 18. So it's 6 plus 18 is 24. Take away, now we put in y equals 1, 2 plus 2. Okay, so we take away 4, and the answer is 20. Okay, so the volume under that surface of the function x plus 2y in this region S, okay, is 20. All right, so that's an easier example where our region is straightforward and rectangular. Okay, but things become more difficult. We have to think about the limits in a more careful way once we have different types of regions. And yes, you can check that rather than doing the integral of dx first and then dy, that the integral of dx between 0 and 2, so you do the dy integral first of the function between 1 and 3. Okay, you can check for yourselves that this integral will give you the same result. All right, it's a couple of lines of work. Okay, so on to another example. So now for an example where our region is not a rectangle, let's think about the region S defined by, okay, so it's going to be a triangle. This is X, this is Y. And we're going to think about the triangle that goes from X equals 0 to X equals 1. And this is the line Y equals X, okay? So this region is our region S. So S is defined by X goes from 0 to 1, but Y goes from 0 to X. Okay? So 0 to 1, and then Y goes from 0 up to X. Alright, so what's our integral here? We've got a double integral over S, function of X and Y, dx dy. Right, so in this case we can write our integral in two ways. We can first think about the integral dx, the integral of f of x, y, dy. We need to think about the limits. So we're going to integrate over y, and y can go between 0 and x. Okay, and then x goes between 0 and 1. Alright, so what we're saying is that this first integral, basically we're splitting up our region into strips at some x. Okay, so this is an integral with respect to y for some x. Okay, so that's this little area here, okay, which goes from 0 up to x. All right, and then we do the integral dx, okay, and the domain or the range of x covered is between 0 and 1. Okay, so we count up all the little strips at the different values of x, and we get this. Okay, we could also think about going the other way. Rather than strips like this, we could consider a constant value of y, and we think about a strip that's horizontal. Okay, and then we add up all these horizontal strips. And you can see for yourself, for an example, that we can also write this as, instead of dx, we do the dy integral last. Okay, and first we do the integral along x. Okay, so this little strip here. So in this case, we need to rewrite our limits. So in this case, we have that x goes between, to the lowest bound of x for any value of y is y. Okay, so if we're at this height, then this is our starting point for x, which is y. Okay, and the end point is 1. And y can go between 0 and 1. Okay, y equals x. So 0, y to 1. Okay, so these both define the same triangular region. Okay, this is needed for the limits when you do the integrals in this order, and this is needed when you do the integrals in this order. So here we're going from the lowest x to the highest x, and the lowest x for any general y is equal to y. Okay, so that's our lower limit, and our upper limit is 1. So for all of these horizontal strips, the upper limit is 1. Alright, so we get the area of this little strip here, and then we need to sum up over all the areas of all the other strips. So the strip up here looks like this. It goes from x equals y at this height up to 1. Okay, so we count up all these horizontal strips that are of different lengths. Okay, the different lengths are covered by these limits. So y takes the value from 0. Okay, we're going from this point up, and we're considering all the horizontal strips up the y-axis until the horizontal strip at y equals 1. Okay, and you can check for yourself for some functions. I don't know, try the function that we looked at previously. X plus 2y, this house with a monopitched roof. Check that these two things give you the same result, i.e. that the integral 0 to 1 dx, 0 to x of x plus 2y dy equals the integral where we do the integral over dy second. We do the integral over dx first. Okay, so you can check that these two things are the same, and you'll find that one will be more straightforward than the other. Okay, and this generally happens when you've got different limits. Okay, and in some cases, one order is easier to calculate than the other, but they should give the same result. Okay, so I'll leave this as an exercise for you. We'll just think about one final example. Okay, so one more example. Let's have the integral of the function just f of xy equals xy. Okay, so let's have the line integral around some region S, which we'll define in a second, of xy. That's our function, dx dy. Okay, where S is the region defined by the curve y equals the square root of x. Okay, between y equals 0 and 1. Okay, so this region here. Okay. So again, this describes the volume under the surface of the function xy in this region. Okay. So if we have the x, y, z axes drawn, then this region y equals the square root of x. It's this little region here. Okay, and we've got x times y. Okay, so we're thinking about the volume under this surface defined here. Okay, whatever the function of x times y is. So we're going to have little columns with volume that we're going to add up in this region. Okay, so we can do this via an iterated integral. We can think about doing the integral over dx first. So that means the integral over dy is outside. Okay, xy dx. We need to think about the limits. So how do we define this region? So if we're thinking about the limits of x starts from 0. So everywhere in this region, we can start from 0 and then we go to this line, which is given by x equals y squared. Okay, so if you're at this value of y, you start from x equals 0, you go to x equals y squared. X equals y squared. Okay, so the lower limit is 0, the upper limit is y squared. Okay, so we're thinking about little strips like this, and we add them all up from y equals 0 up to y equals 1. So the limits on y are 0 to 1. Okay, and we can just do this integral then. You know how to do this integral. two separate integrals, basically. Okay, so the integral of xy dx is equal to x squared over 2 y. So this is the integral keeping y constant. Okay, and we evaluate this between x equals 0 and x equals y squared. Okay, so this equals dy 0 to 1, that's unchanged. Now everywhere we see x, we put in y squared. So this becomes y to the 4 times y divided by 2. Okay, which is just the integral of y to the 5 over 2, which is y to the 6 over 12. Okay, integral of y to the 5 over 2 dy between 0 and 1, which is just y to the 6 over 12. Evaluate it between 0 and 1, and this is 1 over 12. Okay, so this is the volume under the surface defined by this region. So that's defining the region in this way. But we can also swap the integration order. Okay, so instead of this, where we do the integral over dx first, the integral over x first, and then the integral over y, we can think about writing it as an integral over y first. Okay, and the limits now are different. Okay, and that's what you have to think about. You can reverse the order of integration, okay, but this changes the limits. So the region is defined in the same way. It's just this shaded area. Okay, but how we define this area is now different. If we do the integral over y first, then what's the lower limit in y? Well, if we're at this value of x, it's here. If we're at this value of x, the lower limit of y is here. If we're at this value of x, the lower limit of y is here. Okay, so the lower limit of y is given by this curve, which is the square root of x. Okay, and the upper limit of y is 1 in all cases. Okay, so this region can be defined by going from the line y equals root x up to y equals 1. And then considering all these lines from x equals 0 up to this point here. Okay, when y is 1, this means that x is 1. Okay, so here's our limits. And if you do this integral, so if you do the integral over y first, and then the integral over x, you'll get 1/12 again. Okay, or you should get 1/12 again. Okay, so far we've been thinking about the double integral as being the volume under a surface, okay, defined by the region in the xy plane. But you can think of it differently. You can think of this integral, some function of x and y, dx, dy, as equaling the mass of the region S in the xy plane. Okay, so if you think of this as the mass per unit area, okay, and we know that this dx, dy is an area element. Okay, so this thing equals the mass of region S. Okay, where the region S is defined in the xy plane. Okay, so what's the mass of this little strange lamina or region? Okay, to find it, we can do this integral. Okay, where now instead of f representing the height above the xy plane, it's the mass per unit area in this region. Okay, and we split it up again into little chunks, little rectangles, dx, dy. So rectangles of area, dx, dy. Okay, and we can calculate the center of mass. So the center of mass, okay, so if you cut up a page into some arbitrary shape or a bit of cardboard and you try and balance it on your finger, okay, then you want to find the center of mass. Okay, otherwise, if your finger's not on the center of mass, it will just topple. So the center of mass is a coordinate x bar, y bar, where x bar is equal to the integral, so the double integral, over the region of x times the function which describes the mass per unit area, dx, dy. Okay, this double integral, divided by the total mass. Okay, the total mass is this integral. Okay, it's the mass per unit area times the area, all summed up. So this is x bar, and y bar is the same except you replace x with y. Okay, so if you want to calculate, if you want to cut up a bit of card and you find the center of mass, this is how you do it. Okay, so double integrals have use not just in terms of finding volumes under surfaces, but also in terms of centers of mass, calculating mass, or even calculating the charge, so the electronic charge on a sheet. Okay, and it may be different at different points of the sheet, and this function will tell you what the charge is at different points on the xy plane on the sheet. Okay, so this is just a different way of thinking of it rather than the volumes under a surface. All right, okay, so we're going to move on to section 4.4 now. Okay, keep going.